Eric Archer here from TI, and today we're going to explore how changes in temperature and the chemistry of a freshwater ecosystem may affect the fish that are living in that ecosystem, so a stream or a river or pond. To do this, we're going to use a simulation from a file titled Freshwater Chemistry, and that can be found and downloaded for free at our website at www.scienceinspired.com. And to use this file, you'll need our software, which is the TI-Nspire CX Premium software, which can be downloaded from our main site, which is www.education.ti.com. All right, so let's get started. All right, so we've got the file titled Freshwater Chemistry opened up in the TI-Nspire CX Premium software. You can also use this file as well as any file from scienceinspired.com using the software like we're doing today, or you can use the TI-Nspire CX graphing calculator or the TI-Nspire CX2 graphing calculator. Either of those will work as well. Okay, so next page, page 1.2, we have the first question, and the question starts off, what happens to the amount of oxygen that can be dissolved in water as the temperature of the water increases? Well, before we can get an answer, let's go over a little bit of this concept of dissolved oxygen. So fish, like people, require oxygen to breathe. We have to have O2 to breathe. The way fish get it is with their gills. Their gills are kind of like our lungs, and those gills are able to pull the oxygen out of the water, and the bodies can use it. Like humans use oxygen we breathe in with our lungs. The oxygen gets into the bloodstream and gets transported to the various parts of your body that require oxygen. Fish do the same thing, okay, except they don't have lungs necessarily, they use gills instead. But same principle applies. They have to get that O2 to all the parts of their body. So the way they get it is oxygen is also found in water, fresh water, salt water. In this case, we're talking about fresh water, but it's found in fresh water and salt water. And so the way it gets in there is by groundwater discharge. So water that's moving, like a stream or a river, tends to have a good amount of oxygen just from the motion of the water interacting with the atmosphere. And so the fish require this. Now, the question asks, what happens when what's the effect of how much oxygen is dissolved in the water when the temperature of the water goes up? And so a lot of folks may think that, well, the warmer the water, the more oxygen we can have in there. And that's actually incorrect. It's the other way. The colder the water, the more dissolved oxygen, the more oxygen can be dissolved in colder water. And it has to do with how much energy is in that body of water. So the warmer the water, the more energy. The more energy, that means all the molecules, including oxygen, are moving much faster, and so they're able to escape the water and get back into the atmosphere. And so this question is asking because most of this activity deals with dissolved oxygen and temperature. And so the choices are A, there's less oxygen in the water, B, there's more oxygen in the water, C, there is no change in oxygen in the water, so we're saying that C is assuming that temperature has no effect and dissolved oxygen amounts. And so the actual answer, like I mentioned earlier, is going to be A. So there is less oxygen in the water, the warmer the water gets. All right, so page 1.3, this is our first simulation. There's two in this activity. Directions are, we're going to play the start button, we'll adjust the water temperature sliders up and down. We're going to move through the entire range to collect data. Now I'm going to skip around a little bit here, and I'm going to kind of cheat. We'll run through the simulation a couple times, but then I'm going to show you a data set to give you a reasonable idea of how the relationship between temperature and dissolved oxygen. And DO stands for dissolved oxygen. And a little bit later, we're going to look at a graph of DO versus temperature. All right, so let's try this out here. So the water temperature is 25 degrees, and currently it's saying that the DO reading is 8.26 ppm. And ppm stands for parts per million. So out of a particular volume of water, out of the million molecules that are in that water, 8.26 of those are dissolved oxygen. That's basically what that means. And so I'm gonna crank the temp down as far as I can. Okay, and we'll hit start. All right, so these little white dots are meant to represent the amount of dissolved oxygen that's in the water. I'm going to go ahead and continue to raise the temperature. And you can see the numbers changing as I raise the temp. I'm at 12 degrees C. We're under 11 parts per million of DO in the water. Let's see, man, it's going down pretty good here. And I don't recall how far up we can change it. Well, look here. So at 40 degrees is our max. Okay. So 40 degrees C, we have 6.39 parts per million. So you'll notice there's less white dots to kind of represent what's happening there. I'm going to press pause. And let's go check out this data table here. So I have a column that says temperature and a column that says DO. Okay, and as we kind of move through the parameters, or sorry, the values, you can see there's a pretty good relationship here. As you go up in temperature, your dissolved oxygen actually goes down. So anyway, so there you go. Looks like I collected a little more data than I was supposed to, but it won't affect the graph on the next page. So the graph is showing dissolved oxygen versus temperature. And so what we see here is at 0 degrees C, our DO value is 14.56, remember ppm, parts per million. Okay, and the temperature is at 5 degrees C. We had a ppm value of 12.78. 10 degrees C, 11.3, 15, 10 ppms. So in a 15-degree change, we went from 14.56 to 10.09. And so if we go to 20, we're under 10 now. 25, 8. And so you get the idea here, right? So at 40, we're down to 6.39 parts per million. So we went from 14.5 roughly down to 6.3. That's a big shift. That's a big drop. All right, so let's see what these questions are asking us. Is the relationship between temperature and dissolved oxygen linear? Well, that means that the graph would have a straight line from here to here. Now you can see, I'm sure, there's a subtle curve in the data, in the graph, and so we're going to go ahead and say no, it is not linear. Support your answer by explaining how you interpreted the data. Okay, so let's go take a look back at the graph and see what we see here. So when we look at the data, we have a lot of data points. They're going from 0 degrees C to 40 degrees C, so 40-degree temperature change. And over that 40-degree temperature change, we saw the dissolved oxygen go from 14.5 parts per million down to 6.4 parts per million. So we're just going to round this up to 6.5. So you're looking at an 8 part per million change over a 40-degree temperature change. And so the data, it's not straight like a straight line. It has a subtle little curve to it. And so initially what that means is the dissolved oxygen, as temperature increased, dissolved oxygen dropped off a little faster, and then as the temperature got higher and higher, there was less dissolved oxygen, less dissolved oxygen, less dissolved oxygen, and so on. So you could think about this as, well, here, when the temperature is low, I've got a lot of dissolved oxygen. As I increase that temperature, the amount of dissolved oxygen that I have left that's available to leave the water becomes less and less and less and less and less. And so that's why you have this subtle curve here. It's just because as you get rid of dissolved oxygen as the water warms up, you have less and less of it that's available to be removed. So that could explain some of the curvature we see in this graph. It just doesn't, dissolved oxygen doesn't decrease at the same rate that the temperature increases. So that's how I would interpret that data. All right, page 1.7. As the temp of the water increases, the amount of oxygen dissolved in the water also increases. Well, we saw in the graph that is not the case. As the temperature increases this way, the amount of dissolved oxygen doesn't go up. Instead, it goes down. So that means that they have a bit of a negative relationship. So as one goes up, the other goes down. And that's what we saw in the graph. So we're going to say false. All right. Next page. Predict the effect of an increase in water temperature on fish living in the lake. Well, before we answer this question, let's think about what we know so far. What we know so far is that fish require oxygen to breathe, just like people and other animals. So if there's less oxygen in the water, it seems reasonable to conclude that there may not be as many fish in that body of water, just because there's not enough oxygen to support, a lot of fish or a lot of types of fish. And that's the other point here, is that we'll see in the simulation coming up that not all species of fish respond the same way to changing chemistries or changing temperatures of water. So anyway, so the question says, predict the effect of an increase in water temperature. Well, you know by now that an increase in water temperature also means a decrease in, that's right, dissolved oxygen. So if there's a decrease in oxygen, that means there should be a decrease in the amount of fish. This says the fish would swim faster. Well, if there's less oxygen, that means they can't get as much oxygen to their muscles, therefore they're probably not swimming faster. Second option is the fish would have trouble breathing. Well, that sounds reasonable. Third option is there would be no effect on the fish. Well, we know that's not true. If your oxygen was cut off, or if you've ever been in a swimming pool or in a body of water like a lake or something, you try to hold your breath underwater, you can only do it for so long, and then you have to pop back up and get a deep breath of water, deep breath of air to replenish the O2 your body's already used up. So we're going to go for this option. The fish would have trouble breathing. Next page. In this experiment using the simulation, you will change the temperature levels and observe the effect on the fish population, number of fish species in the lake. Like I said, we're going to look at different species in this lake. To change the temp during the simulation, select pause. Keep the pH the same in this experiment. So why do we want to keep the pH the same? Well, how would we know what effect, if the fish decrease or increase, how would we know if it was because of pH or temperature, right? So by controlling only one variable at a time, we'll see if there is an effect, we'll know it's because of temperature. And later, when we look at pH, we'll know it's because of pH. So you got to control one variable at a time. You can't change two variables at a time, because then otherwise you don't know which variable caused the change. All right. So here we go. We've got a nice little. We got our goggles on. We're under the water. We're checking out the fish. pH is at 7, which is neutral. Okay, so pH can go from 0 to 14. 7 is in the middle. 7 is your neutral pH. It means pure, clean water. The temperature is at 23 degrees Celsius. We see that the population of fish, which is the number of fish, is 100, and the different species of fish is 6. Okay, so I'm gonna go ahead and start us. We're only changing temperature in this one. I'm gonna start us down at 10 degrees C. Press play. All right, water's a little chilly. Not something you want to swim in necessarily. So we got a little oxygen bubbles kind of bubbling up there. Really nice fish, beautiful fish. I wish I had my fishing pole. But it looks like there's not a lot of change here. So I'm going to pause this. I'm going to bump this up to, I don't know, try 15. Okay, so far so good. Still have 100 fish and 6 different species. I think that was a salmon that just swam by. I'm going to bump this up until let's try 25. All right, we have a little change here. Okay, so the water's getting warmer. The good news is we still have all 6 species, but looks like our population numbers decreased a little bit. And let's bump it up a little bit more, we'll say 30. Oh, wow, okay, big effect here. So population dropped to 75, and now we only have 4 species of fish. So we lost 2 of the species. It's too warm for those fish. There's not enough DO in the water. We're going to pause. Let's bump this up to 35 now. Uh-oh. That's unfortunate. So it says there's 12 fish, 1 species. And so I assume if we go all the way up to 40, everything's dead. All right, so fish are dead. By the way, dead fish usually don't do this, but we just put that in there for effect. And in reality, no fish were harmed in this simulation. Okay, so I think I messed that up a little bit. I wanted to go up to 32. Okay, we lost 3 species. Population is about 2/3 of what it was. 33. Wow, look at that. 1 degree difference, and we lost 23 more fish, and we're down to only 2 species. And then 34. 34 is about the same. Yep. And let me pause that. And then 35, we saw bad things. So 12 fish, 1 species left. It's just this, whatever this is. All right, so there you go. Let's take a look at some questions. What is the best temperature range for fish in this lake? Well, I did a little sort of cooking show approach here, and so I'm going to go ahead and show you some of the data right now, and we'll take a look at that. All right, so I have a little blow up here of the data table. So if we were to run the simulation through all of these different temperature changes, these are some of the numbers we would see, and so I wanted to show that to you. This is temperature, number of fish in the population, and by the way, each column kind of wraps around so this is the first half of temperature, this is the second half. Number of fish in the population, that's the first half, and then this would continue into the second half and so on. And then the third column is number of species in the population. So 6 was the max number of species. 100 was the max in terms of the number of fish in the fish population. And we saw that up until from 10 degrees to 22 degrees, we have a really strong population of fish. We have multiple species. Everything's looking good. We hit 24 degrees C and we saw a drop off in the population numbers. As the water warmed up every couple of degrees, you see a pretty dramatic drop off, especially from 28 to 40. We go from 82 to 75, 66, 43, and then from 34 to 36, forget about it. It's 43 to 12, and then 0, 0. So, and then the number of species in the population. What this means is, of the original 6, especially down here at 34, 4 of those species of fish could not hack it. It was just too hot. There wasn't enough DO in the water, and they require a certain percentage of dissolved oxygen in order to survive. And so, you know, for those fish, it's like holding your breath the whole time. They're basically asphyxiated in the water because there's just not enough O2. All right, so hopefully that makes sense, and we'll move on to the activity. All right, so that question, what is the best temperature range for fish in this lake? Well, I think we saw that between 10 degrees C and 22 degrees C, we had a large population, and we had you know, multiple species of fish present. So in terms of biodiversity and population, 10 degrees to 22 degrees would be probably the best answer here. Do you think the pH of the water will affect the fish in a lake? Well, I probably wouldn't be asking you if it didn't. And so, you know, yeah, definitely the pH is going to affect things. For example, we all drink water. Water is around between 7 and 8 on the pH scale, but you don't drink things that are super acidic. Down in the 1 or 2 range, that would do some damage, and you certainly don't drink things that are up in the upper range, like bleach or cleaning supplies in the basic level. So I think if you change the pH of the environment where fish live, it's certainly going to have an effect. All right, next page, go back to the simulation page, and this time instead of changing temperature, we're going to leave temperature alone, and we'll probably keep it at, I think we'll keep it at 22 because that was the warmest the water could be without losing any of the fish population or the number of species. And we'll see what changing the pH does. All right, so let's check that out. Poor fish. We got to reset this here. There we go. Everybody's back. All right, we'll just leave it at 23. It looks like we still have 100 fish total and amongst the 6 species of fish. Okay, so I am going to, well, let's just go ahead and press start. And I need to pause this, don't I? So we still have 106. 100 population, 6 species. We change this by 1. Oh, wow. Wow. Okay, so we decreased the pH to 6, which is slightly acidic. And we lost 45 of our population, 45 fish, and we cut our number of species in half just by changing the pH by 1. All right, let's try 5. Yeah, so we lost another species and we're down to 30. Not good. 4. Man, all right, we have that the gray background again. Can never be good. All right, so we're down to 10 in the population and only 1 species remaining, although I didn't see anybody swim by. Oh, there's one. So it's that same fish. Well, that fish is it's pretty hardy. It can handle a low pH and as well as a high temperature. But it can't handle a pH of 2. That's basically, it's pretty intense. Okay, so let's do this. We're going to stop that. We're going to pause that. We're going to bump this back up. This time we're going to go to 8 because we started at 7. Everybody was happy at 7. Let's see what happens at 8. 8's not so bad. Still 100 in the population and species. There are 6 species. What about 9? Wow, okay. So we hit 9. We lost half of our population and half of our species. So they're not liking that too much. Okay, and so pH of 10, it's still that very hardy fish. I don't know what that fish is. 1 species left and 20 of them in the population. So I wonder how high up we can go. Down to 8 and still that same species. 12. Let's try 12. Nope, 12 is it. So anything below 3 and anything above 11, no fish can survive. No population of fish can survive. All right, so the best temperature range for fish, we already did that one. Let me go back down here. All right, so in what pH range was the number of fish species the highest in this lake? We saw that it was between 7 and 8. So the answer would be C. And let's run a scenario past you. Let's say you're working for your state's DNR, which is Department of Natural Resources. Every state has a DNR. You have just tested a freshwater pond. If it is a healthy body of water, what range of values would you expect for its temperature and its pH? Well, we saw on the temperature side, if you guys remember, we were between 10 to 22, actually 23 degrees C. And then on the pH range, we had a pH range of 7 to 8. So those are our optimal conditions for this particular body of water. And the simulation is just that. It's trying to represent nature, but it's still a simulation. I mean, you've got the cartoon fish and the cartoon water. But so just keep that in mind. This is a great way to kind of experiment in a virtual sort of ecosystem, but this doesn't nearly cover every single variable. There are other variables at play here in aquatic ecosystems. The time of year, what season you're in, is there wind? because wind increases the amount of dissolved oxygen in the water because it disturbs the surface of the water and it thereby increases DO. You know, during the day it's hotter than it is in the evening, and so there are a bunch of other variables to think about. But for this activity, we wanted to just make sure you understood that dissolved oxygen is required by aquatic organisms, and that changing the pH has a negative effect on those organisms, and temperature that's too hot decreases the amount of dissolved oxygen, which has a negative effect on the species, number of different types of fish, and how many fish are in each of those species in that aquatic ecosystem. All right, well, so that's it for me. Hope you enjoyed this lesson, and check out more of these kinds of lessons. Most of them have some kind of little simulation like this at www.scienceinspire.com, and hope to see you again, and check out our YouTube channel, TI Calculators, all one word. All right, thanks so much. Have a good day.